um, the critical thing that I want you to think about is I want you to think about the limitations of each method and why one would choose one over the other versus why one would not choose one over the other. And, right now there's a huge push, and I mean huge push. I mean like several hundreds, probably a few $100 million from the NIH to improve brain mapping methods in humans because they are so basically abysmal. I mean, compared to what we need. Um, and honestly, that amount of data, even from one person from one session, would be to actually see every neuron. You couldn't process it. You couldn't really, So it's kind of a fundamental limitation is the amount of data processing and everything. But basically, the first what quote unquote brain mapping neuroimaging methods, aside from cellular methods like histology, um, were EEG. So electroencephalogram was invented in the late 30s in Germany. Um, and basically, they had one or two electrodes in the first setups, just one or two electrodes. So you saw like this average waves. The alpha wave was the first one discovered because that's really prominent. If you close your eyes, you can see it on the screen in real time because it's so strong, especially if you're sleepy. And then there's beta and gamma and delta. And all of that, you know, they're divided into certain, you know, frequency bands. So those waves, alpha waves, for example, are usually defined from 9 hertz or 9 times per second, peak to trough, and to 13, 14 hertz, maybe, usually 12, maybe. It's, you know, and these things aren't even settled now. It's almost, I mean, it's 80 plus years later, and we don't really have, even with all the data that has been collected, a consensus view on what frequency bands are, and what the frequency bands do, and everything. They have associations, but they're not strong associations. One of the critical things that EEG is good for is evoke potentials. So basically, you flash a light, and then you see a brain deflection, and you can measure the time that it takes for the beam of light being emitted from the screen to it being processed, in the visual cortex, for example. But again, it's very crude. So with EEG, the spatial resolution is something like several centimeters, a few inches, is really what your spatial resolution is. So you can basically say you have the front part of the brain, the interior, you've got frontal, mid, and rear, and then you can have left or right, basically. So it's very useful for timing, but it's not very useful for figuring out what's going on inside. And then there's another huge issue with EEG that basically is, it's called the inverse problem. And the inverse problem, which I don't know if they go into it in this book, is a little bit complicated, but basically, so you're measuring these electrical deflections, these very small electrical deflections that are presented on the scalp. So you're measuring from the scalp. So you're not next to any neurons at all. you're not adjacent to. I mean, the closest neurons are probably, even people with very thin skulls, probably, I don't know, a centimeter, 2 centimeters away minimum. Um, and so the inverse problem basically says that it doesn't matter what the so you can have different firings of neurons, different groups of neurons firing, and you'll get the same picture on the scalp using EEG, the exact same picture on the scalp. So it's not a solvable problem. People have tried to solve it by doing a bunch of stuff. The best approach I think is probably combining EEG and fMRI, but that is also technically very difficult, and very few people do that. And you have to have the right paradigm and everything. So that's the EEG. That's EEG. So then positron emission tomography largely came out. And positron emission tomography, basically, you give somebody a radioactive tracer, usually give them a sugar with a radioactive tracer on it, or water, or fluorodeoxyglucose, or you can also do tracers that bind to certain receptors. So for example, for the opiate receptors, they make a very, very tiny amount of carfentanil, and then inject it into the person and, map their receptors. So, like, you can't even see the amount that they make. And the limitation with positron emission tomography is both spatial resolution is not great, 2 to 3. The timing, and basically you have to have somebody doing the same task for like a minute to get any signal whatsoever. And then you have to expose people to radioactive nuclides. And you also have to have a particle accelerator on site. So yeah, yeah, like you have to have a physicist that's running a particle accelerator on. It's a small one, but I mean, it's still a particle accelerator because you have to, because the radionuclides, in order to be able to image them, they have to have very short half-lives. So like these like radionuclides have like half-lives of minutes. So basically you inject it, it's warm because it's radioactive, and it goes, you do your task, and then you get to do it again and get to do it again. So, there are very few places that do this regularly. I know Hopkins definitely does it. I think the University of Maryland does now, because there was a new machine that came out that combined MRI and positron emission tomography. And I think they got that scanner. But yeah, they're very expensive experiments to do, because you have to make a radionuclide, which is not cheap. And then there's functional magnetic resonance imaging, which functional magnetic resonance imaging it images the bulb response. So it's a blood response. So you're interested in looking at neural activity, but you're looking at blood flow. So it's clearly indirect, one. And two, blood flow modulation is really slow compared to neural activity. So neural activity, you can have the whole event, the whole neural event over in 150 milliseconds or 100 milliseconds. And the peak of the activity for blood flow will be at 5 seconds later. So, there's obviously there's limitations on how you can, and then it doesn't go away until like 10 or 12 seconds later. So we're dealing with this with a study that I'm working on, doing the data analysis for, that I had designed and ran. and things are bleeding into one another, and you don't get a huge, very clear picture. There are ways to improve that timing. You can use a very, very strong magnet. There are magnets, I think there are a few magnets in the world that are 9.6. So the normal magnet that you go to the hospital is a 1.5 Tesla, and it can be even lower. But frequently it's a 1.5 Tesla. The research magnets that I use usually are 3 Tesla, which are so double that strength. And then there's a research magnet at Hopkins. I think the strongest magnet in Baltimore that is used for humans is the research magnet at Hopkins, which is 7 Tesla. And then there are these research magnets that like literally people make. Like I was reading an article, like literally a group of some of the best MRI specialists in the world got together and spent $20 million to make the best magnet. And like, yeah, it's great. It's great. But there's one of them. Nobody can use it except for this group because nobody really knows how it works. And there's another issue. So have any of you ever been in a research magnet before? Like a 3 Tesla? You ever had an MRI? Anybody? Okay. So when you
Not
go,
the same thing that's in the fMRI. I've seen an
yeah,
MRI scanner for fMRI,
right,
so
right, right. So the magnetic field is really strong. So you can't go in there with any metal. You can't have any metal implants. Well, you can have metal implants. They just have to be the right ones. And those are validated on a per person basis, which can be, you never want to be the first one to try. We'll put it that way. We
yeah,
had
we
a
had a
guy,
lot of kids that had braces, and
oh
they
yeah,
had to check with their dentist or their orthodontist, and
right.
yeah.
Yeah, you have to figure out what material it's made out of. And then frequently with braces, like because it's a half circle, I can imagine it would, because you can't have loops of metal. So loops of metal can cause everything to melt. Then, you also like you can't carry a clipboard in there because like just the littlest bit of metal can fly in. Now, in a research magnet, there's another issue about 3 Tesla. When the person that's laying in the magnet, you can start to spin. Like you can perceive that you're spinning because the magnet is so strong it moves your otolymph in your ears. So it's it's a really weird experience. And so, there's limitations. And so you can do pretty good spatial resolution. Temporal resolution for the blood flow is getting there, but the blood flow still lags by seconds behind the neural signal. And usually, the amount of lag that we give it is about 4 to 6 seconds, and then to peak, and then we usually give it another 4 to 6 to recover. So a total of 12 seconds. So you can have stimuli that are separated by 9 to 14 seconds or something, and that makes sense. But otherwise you can't really do anything. Now there's another technology that came on after or about the same time as functional magnetic resonance imaging, which is magnetoencephalography. So they're extremely sensitive. So much sensitive that you have to have a special room built. You have to have a special room built for the MRIs too, because the magnetic field is too strong in the case of the MRI, and the magnetic field of the Earth is too strong in the case of the magnetoencephalogram or graph machine. Where is it? And so these guys are really expensive. well, this is a picture of one. They all look slightly different, but inside this are each single sensor, and they usually have 32, 64, 128 sensor. Each sensor is basically an inverted dewar of liquid helium. And so they're superconducting quantum interference device. Um, they're very sensitive, like basically they're just a very sensitive way to measure magnetic field. So they actually measure the magnetic field of neurons as they're processing through the scalp. And so you get something that's very similar to an EEG. Like this is a 306 channel meg. So you get, these are, give me a second. Just want a simple picture. Is that possible? No, not really. So you get basically something that looks very similar to neurons firing. So, but again, it's there's and the nice thing is that the magnetic field is transparent to the skull. So in EEG, you get all of this spreading based on the magnetic field being transparent to the skull. But these are still, very, they're based on the sensor, the size of the signal, and you're looking at the whole brain. So you can see the events down here in red that are occurring in the visual cortex. But again, this is, this group of sensors for all of the visual cortex in a human, which is a large amount of tissue. Um, so, um, so that's that part. So you can see that it's different, so the one on the left is your magnetoencephalogram, and the one on the right is the OPM sensor, which is, what does OPM stand for? Optically pulsed magnetic detector. So each one of these is a detector. So normally they'll have like a bunch up there. So that's a little bit better because you can have the person not under this huge thing, and it doesn't have to be in a very strongly shielded room. It does still have to be in a shielded room. And you basically get the very similar response. So you can see that this is the beta response to a stimulus, and that's happens over a period of 3 seconds. So that's reasonable for a neural signal. Especially when you have to average it. But again, the spatial resolution is not great. So basically, you have, that's another brain mapping technique that's coming online. There hasn't been a lot of data published from it because I think it's only been around for like the last 3 or 4 years.